of a circle. So we'll go ahead and draw a circle there. Give it a radius r. And then let's go ahead and talk about some part of that, which I'll use a different color here, the red, the length of this arc. So you want to imagine that we've got a little bug here that's walking and wanting to figure out how far did he walk. Or this is maybe the arc on a track, a circle or something like that. And to talk about that length, we'll use the letter S. How long is that? If you were to straighten that whole thing out, how long would it be? I'm going to put a dot here on either end of that arc. And you can imagine that we've gone through and formed some angle which we will call theta. Just out of curiosity, does anybody remember calculating like arc length? Sometimes you do it in geometry. I'm seeing some head nodding.
S equals
yep. You'll use proportions, and that's how we're going to set it up here. We'll say that arc length, the part over the whole, so you don't have to label it, but I like to say part over the whole. So S is the part. The whole thing all the way around would be the circumference, so S over C is proportional to this little angle right here, theta, in degrees, divided by the whole circle all the way around, so 360 degrees, okay? Let's go ahead and do some substitutions here. Formula for circumference. Are we recording?
Yeah, recording.
Formula for circumference. Pi d. I'm going to write it as 2 times pi times r. And the same time over here on the right hand side, instead of calling this angle in degrees, let's go ahead and call it in radians. And you'll see why everything turns out real nice. 360 degrees in radians is 2 pi. So we can sort of imagine those radians sort of canceling. I'm going to multiply both sides by 2 pi r. So S equals theta times 2 pi r divided by 2 pi. What do y'all notice? 2 pi's cancel out. And so S equals, I'm going to write it at, instead of saying theta times r, we'll switch it around, r times theta. And with a little note that theta is in radians. So when you did this, when you found the arc length there of a circle in geometry, you probably set up proportions, which is a pretty fast way of doing it. I prefer this way, right? This is just a simple multiplication. You want to find that arc length? Find the radius, find that angle in radians, and multiply them. And you're done. That arc length is r theta. We'll put a summary over here. Go ahead and apply that real quickly.
Should I stop it?
What's that? No, we got it. We'll at least do one together. All right. So question 1 says a circle has a radius of 4 feet. Find the length S of the arc intercepted by a central angle of 1.7 radians. Do not round any intermediate computations and round your inch near 10. So we've got a radius of 4 feet, so I'll put R equals 4 feet. Central angle 1.7 radians, so theta equals 1.7 radians. What's our formula, class? S equals R theta. Oh. 1 second. So you're going to have, oh, you're good. 4 for the R, 1.7. And I'll let you run those numbers. Go ahead and take care of that. See if you can figure out number 2 here while we take attendance. Oh, that's what.
Oh. If it's free, it doesn't work?
No.
Oh.
It's frozen on whatever. Take care of number 2 and talk about it as a table. Did you get a number on that first one? Six point eight. The question is, what are the units? Say again, Preston? Feet. Why feet?
Because the circle has a radius of 4 feet.
Yep, the radius was 4 feet. Now that was radians, and you might say, why isn't it feet radians? And the answer is because that's just the type of unit that the 1.7 is in, and it's just going to be feet for the. So in case y'all didn't catch that, number 1, that answer you should be having 6.8. I'm gonna walk around and need y'all to show me what you get for number 2. If you finish that, go ahead and work on number 3.
Radians for the unit on that chart.
Yeah, I found the, oh, yeah, yep,
You guys have the answer? And it's a little bit different on this one because this one we're given the F that says you've got the radius. That here they're wanting you to find theta. So when it says an arc length of 5 meters, that's your S. S equals 5, not your theta. Very good number. Okay. Wait of your ladies. All right. Walking around. Hold on. Class, we need to talk about number 2 here. All right, and just got to think about here for a second. Mariah, read to us number 2. Go ahead.
Circle has a radius of 13 meters. Find the radian measure of the central angle theta that intercepts an arc length of 5 meters.
Okay. So, class, let's go ahead and parse this. A circle has a radius of 13 meters. So, I'm going to write R equals 13 meters. They want us to find the radian measure. Okay? So if it's helpful for you, you can write find the radian measure of the central angle theta. So they want us to find theta that intercepts an arc length of 5 meters. So Grace, when it says arc length of 5 meters, how do I note that? What letter did we use for arc length? number one, we were given the radius and we were given the theta and we're trying to find S. This one, we're given the R, we're given S, and we're trying to find theta. But never fear, the formula is still the same. Dominic, what's that formula?
Well, if it's S equals R theta, you just switch it up, see if it
Okay, so you want to
divide.
Yeah, you can divide. You want to solve for theta first, or you want to plug in the numbers and then solve?
I mean, it was easier for me to just solve it first.
Okay, it's easier for you to solve theta. Okay, so you just divide both sides by R. So divide by R, divide by R. So theta equals S over R. So those of you that were kind of struggling, just make sure you're labeling the given information properly. So,
2.6.
oh, S was 2.6? No, hold on. S is 13. No, S is 5. R is 13. I think, yeah. 5 meters and 0.38, so we'll round it to 0.4 for theta. Units? Right, yeah, we're not gonna, yeah. Well, I mean, they ask you find the answer, find the radian measure.
So like when you're using radians,
Yeah, you don't normally write it right, but I'll write it there just to make sure everyone's clear. For the most part, we were really just dealing with radians for this formula, obviously, and then all the other stuff. Okay. Talk to me, class. On number 3, what are they asking for? They're asking for, yeah, the radians. So is that more like number 1 or more like number 2? It's like number 2. All right. Are we ready to move on? All right, let's talk about another formula. Sector area. So back to our notes, we're going to draw another circle. Radius R. Central angle theta. This time we're talking about the pie slice or the pizza slice or the Pac-Man's mouth area. Right? So, yeah, that area right in there, that's the area of that sector. That shape right there is called a sector. And once again, you may have done this kind of thing back in geometry, where we're going to set up the proportion. So part over whole. So the area of the sector, which is the part, divided by the area of the entire circle. I'll put circle right there. Equals, or it is proportional to whatever that angle right there is, theta in degrees, divided by the whole circle. Yeah, 360 degrees. And we'll just play the same game that we did a minute ago. So the area of that sector, so A sub S. If I remember off the top of my head, area of a circle?
2 pi r squared.
Pi r squared.
And just r squared.
My math teacher always would say, I say pi's are round. Some say pi's are squared. Anyway, this is a bad math joke. Theta, we'll say in radians. Once again, instead of writing 360 degrees, we'll write 2 pi in radians. And then just like before, we're going to multiply both sides by the denominator, so multiply left side by pi r squared, right side by pi r squared. So area of the sector is theta over 2 pi times pi r squared. What do y'all notice?
Here's pi.
The pi's cancel out, that 2's still kind of stuck under there. We can pull that out and write it as a 1/2 rather than 2 in the denominator. So 1/2, and then we'll just rearrange this to the standard form, r squared times theta rather than theta times r squared, just moving those around. We'll make a note, once again, theta has to be in radians. This formula works for radians, it does not work for degrees. Why does it only work in radians? Well, because that whole pi canceled out when we had it in radians, okay? So if you have your theta in degrees, then you're gonna have to convert it. But once again, this is a pretty nice formula. It's just 1/2 times the radius squared times your angle. Multiply, multiply, and you're able to find the area of the sector, rather than having to set up the messy proportion and stuff like that. Summary board here, sector area, A sub S equals 1/2 r squared theta. Again, radians. Any questions so far? All right, let's go to the problems.
Yes, freeze. Let's freeze again.
Like, yeah.
All right, number 4. A circle has a radius of 6.5 feet. A sector of the circle has a central angle of 2.9 radians. Find the area of the sector. So here we go, just parsing it regular. So radius of 6.5 feet. So r equals 6.5 feet. A sector of the circle has a central angle, so that's our theta, 2.9 radians. So theta equals 2.9 radians. Find the area of the sector. So write the formula down. 1/2 r squared theta. So that's going to be 1/2 times 6.5 squared times 2.9. Say again. I'm hearing 61.3. Do I have validation? All those in favor say aye. You can see validation back there. 61.3. What are the units? Feet? What'd you say? Feet squared? Let's kind of think about it. Maybe. 1/2 doesn't have any units. The R was in feet, but notice that that was squared. And the theta was in radians. We don't write the radians down. So, yep, 61.3 feet squared. But if you go to Home Depot, don't say I need 61.3 feet squared. Don't say square feet. They'll look at you kind of funny. So, all right. Number 5. Circle has a radius of 2.5 inches. A sector of circle has a central angle. Find the area. That number 5 looks too much like number 4. Number 6. What does that say? Radius of 4.5 feet. Area. A sector has a central angle. Okay. So find the area of the sector. For whatever reason, the randomization didn't affect here, but on your homework, you might have to have a problem where they give you the area of the sector and they give you the radius and they want you to find theta. Right, does that kind of make sense where things are a little bit moved around? Why don't we just come up with some numbers here real quick, class, and figure out what that is. So let's throw a random number for the area of the sector. Will be a reasonable
25.
Units?
Feet.
Square feet, okay. Let's say they tell us that the area of the sector was 25 square feet. And then the radius? What do you think, Robert? He's thinking.
Wait, what are we doing?
You say numbers that work, what might be a number that wouldn't work?
I can't say 5, you say 0.
Okay, yeah, he says can't be 5 because I know I'm going to square the r, and then that would be 25. So yeah, you're right. We need to pick something smaller than 5. Let's pick like 4. Okay, all right, but you do have that 1/2 there. That's fine. Okay, 4. We'll try 4 feet. There we go. Let's find theta. So now the question is, do y'all want to take those numbers and plug them in and then move things around to find theta, or would you rather rearrange first and then plug the numbers in? Rearrange first? Okay. So, Sarah, I want to get that theta all by itself. What do you recommend we do? Okay, move the 1/2 r squared to the other side. How would you do that? Unfortunately, not subtracting because these are being all multiplied. So divide, okay? Now we've got a couple options here. We could dividing by r squared, absolutely. Okay? If you wanted to divide by 1/2, that would work, okay? But it gets kind of, you have fractions of fractions. If, another way, though, would be if you just were to multiply by 2. Because if you multiply this side by 2, then that 2 will cancel out here. And if we multiply that side by 2. So our formula will be theta equals 2 times the area of the sector divided by r squared.
Rounding to the tens.
What's that?
Rounding to the tens, please.
Sure. So 2 times our area of the sector was 25. So 2 times 25 divided by r squared. So divided by r squared.
What'd you get for
Robert, you got a number for us? Say it again.
Robert, what do you think?
Oh, what? Oh, yeah, 3.1.
3.1. Units?
Radians.
Ratings. There you go. We made up our own numbers. Is that realistic? What would a, let's see here. So we had a 4-foot radius circle. What does 3.1 radians look like?
2.25. 16. Isn't 2.25?
It's almost 5. It's close to 5.
Oh, it's 25.
It's
3.14.
yeah,
What,
so
25
pi is
or 2.4?
2.14. Okay, so it's approximately,
Oh,
approximately
yeah.
pi.
Yeah.
All right. So where are pi radians?
Like 180.
180. Okay. So 4. Does that look like about 25 square feet? Oh, I don't know. You get 4 and a 4, so this whole thing would be an 8. And you've got a 4 right there. So if it was an 8, if it was a rectangle, 8 by 4 would be 32. This is a little bit less than 25. I think that's a reasonable approximation. So yeah, I think we're good. All right, now for the fun part. That's what I know what you are. Let's talk about angular speed. All right, I'm gonna ask this question again. So, I know in physics you talk about how fast something is moving. Maybe you're moving at 1 foot per second, okay? Maybe you're moving at 2 feet per second. The question is, how do you talk about how fast something is rotating. And what units do you use? Alright? Now, RPM. I'm not talking, if y'all look at me real quick, I'm not talking about something that's even rolling on the ground right now. Because if it's rolling on the ground and moving, then like a car, then it's still going. I could say, it's traveling 1 foot per second, or 2 inches per second, or 90 miles an hour. I'm just talking about something that's just spinning. Okay? And then what we want to see is, if we talk about something that's spinning, can we then relate that to how fast it's moving? And the answer is absolutely. Alright? So, we want to talk about linear speed. And this new thing of something that's just spinning around in a circle, it's a real fancy name for it. Rotational speed. Linear speed, also known as linear velocity. Sometimes back in like 8th grade, you called it the rate, like distance equals rate times time. Now in high school, we talk about rotational speed. Sometimes we'll talk about it as rotational velocity. Sometimes even angular velocity. So you hear all these phrases, but it's all the same thing. How fast is it spinning? If y'all look at my arm here, I'll try to demonstrate. So maybe I'm going 1 rotation a second, 2 rotations a second. That's what we're talking about. Once again, back there in the linear speed, what are some of the units? We mentioned them earlier. For linear speed.
Radians.
Oh, linear. In a line. Meters per second. Feet per second. Keep going. What are some other ones?
Miles per hour.
Miles per hour. So we write that. You can write that as miles per hour, or you could write it as mph, which is actually a pretty good analog for what we're going to do over here. So that's because you talk about how far something traveled in a given time. Now we're going to talk about how much it rotates in a given time. So when you talk about measure rotations, how do we measure rotations? Radians or degrees. So you can talk about it in degrees per second or radians per second. I just traveled 2 pi, here we go, 360 degrees per second. 1 Mississippi, 2 Mississippi, 3 Mississippi. 720 degrees per second. Or you do radians, right? 2 pi radians per second. 1 Mississippi, 4 pi radians per second. What's the one that you guys said earlier? The very first one? How fast something is rotating? Revolutions or rotations, the same thing. Revolutions per minute, which we sometimes write as RPM. So I kind of like that MPH there. Your linear speed, is the distance that you travel divided by the time that it took. Your rotational speed anybody want to make a guess? Okay, rotation. We'll say maybe the angles that it goes through. So the angles. The technical term people use letters the angle that is swept through, because it's kind of like a sweeper thing. You know, so the angle that is swept divided by time period. In physics, you probably use the letter V for velocity. Talk about the speed. So velocity, and then this is delta x, so delta meaning change in, over delta t. I think the other day when y'all were asking about this, y'all know delta. So I think this is a familiar formula, right? So, well, we've got to have a different letter to talk about rotational speed. And so just like we use theta for the angles, we're going to use omega. Greek letter omega equals delta theta over delta t.
So lowercase omega.
Yes, lowercase omega. All right. Any questions so far? All right. I'm going to leave this. And we're going to talk about how fast something is moving. So, go ahead and hold up your little car now, and if you can, try to spin those wheels freely. Hopefully, you don't have too much friction there. Now, what I want you to imagine is that there has been a little flea or gnat. I'm not gonna say yes because I hate it. Something has landed, okay, a fly maybe, on the edge of your wheel, okay? And he goes for a ride. Ready? Woo! Right? He goes all the way around, okay? And he gets off and he tells his friends, I just went for this crazy ride, I was going so fast. And they would say, well, how fast did you go? Right? Okay? And he would say, well, I went around at 2 radians per second. And they're like, what does that mean? You know what I mean? Because 2 radians per second, like that's you're just talking about going around in a circle. Like, what would that feel like if you were like traveling straight? You know what I mean? Like, is that like the equivalent of like 2 inches per second? Because that's awesome. Like for, I guess that'd be fast for a fly. You know what I mean? So like, well, how fast did you really go? Like, give us something that we can like be more familiar with. And so that's what we're gonna do. We're gonna connect going around in a circle, okay, with straight line travel, okay, and velocity. So here we go. So if a wheel is rotating freely, so it's not like, it's more like a circle or whatever, but if it's rotating freely, so it's not on a surface, it's just spinning. And he's going all the way around there, who knows however many times. And he tells his story, he's like, whoa, you could think about it in terms of going here. We could talk about his linear speed. His linear speed would be the distance that he traveled over time. Now let's connect this to something that we talked about at the beginning of the lesson. Close. What is this distance that we talked about right here? This all the way around it would be the circumference, but what if it was just like partial?
The sector.
Not the sector, because that was the area.
The arc.
The arc length, okay? So the distance that he travels is this arc length. That make sense? So if I travel this far, then it will only be this much of the arc. If I travel all the way around, then it'll be one circumference. But so I'm going to say it's the delta S for the delta arc length divided by delta T. we have a formula for the arc length. What is it, class? S equals R theta. So I've got delta and then R theta and then over delta t. Now when I've got that delta, that means change in. Does the radius change? No. So I'm just going to apply that delta to this theta. So it's R delta theta over delta t. Delta theta over delta t, does that look familiar? This formula right here. So R times omega. We'll make a note. Radians per second, because unfortunately we're out of time. But here we go. We'll pick this up tomorrow and do some practice problems. But you know the formula now. The linear velocity of a particle on the circle, the little fly guy traveling around the wheel, his linear velocity is R times omega. All right. Here in a second, we're gonna take your little wheeled vehicles and we're gonna put them in a box in the back. Okay. We talked about 3 formulas today, class: the arc length, the sector area, and the linear velocity. Tomorrow we'll just wrap up and handle a few problems on that. And move on. Just take all your little fun wheeled creations and put them in one of those boxes in the back.
Dang. Energy right there. That's the whole wind turbine.